fails to exist today. So we're going to start off with an easy function, because we like to start off easy. Right? F of x equals absolute value of x. So let's graph that. I know that that's not difficult for calculus students to graph, so let's just graph that. Now we all know, right, that an absolute value function is a piecewise in disguise, right? Well, is it continuous, first of all? It is. And it's a piecewise. So let's write it out as a piecewise. It's going to be f of x equals, the break here is going to be at x equals 0, right? Because that's when it changes. It behaves like x when x is greater than 0 and negative x when x is less than 0. And it truly doesn't matter which you put the equals on, and we'll just put it on the first one because it's first, right? So, for a function to be differentiable, that's a big word. What does it mean to be differentiable? That means you can take its derivative. In order for it to be differentiable, it first has to be continuous. So can we say for differentiability, there are two things we have to check. First we have to check, is f of x continuous? And can we check that? Yes? I think everybody here can see that that's continuous. And then the second thing we have to check is the slope from the left at every point. And where is it going to have trouble with the slope being the same from the left and the right? At x equals 0. So the slope from the left, that means f prime of x has to equal the slope from the right. And in this case, if we were going to write a function for the derivative, that would be f prime of x. What is the slope of this absolute value function on the left side of 0? It's -1. So what we're going to do is we're going to graph f prime of x here underneath. And we say that it is -1 on the left side of 0. So for every point to the left or less than 0, the slope is -1. You agree with that? What about the slope to the right? The slope of the line on the right is 1. So for every tangent line to the right, the slope will be 1. So what happens at 0? We have a discontinuity in the derivative, don't we? And it has to be open here because you can't decide which slope. Will it be a +1 slope or will it be a -1 slope? We're approaching two different slopes from the left and the right. The slope from the left is -1. The slope from the right is +1. So do you see how this is not equal here? So we would say that it's -1 from the left and it's 1 from the right. Therefore, it's not differentiable at x equals 0. Now let's write a piecewise for the derivative then. Can we read that off of this graph? What would it be? For x greater than 0, it would be 1. And then for x less than 0, it would be -1. And you can't put in equals here because you don't know which slope to choose, right? We call this a corner. It's like a corner. The slope turned the corner, yes? It's -1 and then all of a sudden, bam, it's 1. There's no smooth transition, is there? So this is called a corner. So derivatives fail to exist at corners. And they have to exist in 4 places. So this is place number 1 at corners. Now let's look at the next graph. The next graph is going to be f of x equals x to the 2/3. That's a power function, isn't it? You remember what it looks like in the first quadrant if it's to the 2/3? It looks like a, not like a parabola, but a square root. And if you plugged in 0, you plug in 0, and then you plug in 1, you get 1. And then it looks like that in the first quadrant. And then if you were to rewrite this in radical form, it would be the cube root of x squared. And so it has domain for all real numbers, right? Because you can plug in a negative number and square it. Well, and you can take the cube root of anything, right? So what happens to the left here? What kind of symmetry do I have? Even. So there it is. So let's talk about, is this function continuous? So for differentiability, f of x is continuous. We got to check that out. And can you check that? We can check that it's continuous. What about the slopes? Now this is where it gets a little bit interesting. We have to figure out if the limit as x approaches. Now where do you suppose this one's going to have trouble? At 0, because there's nice smooth slope transitions. So 0 from the left of f prime of x has to equal the limit as x approaches 0 from the right of f prime of x. So what's happening to the slopes on the left? What kind of slopes do we have of tangent lines? Negative and getting big negative. And then on this side we have positive headed towards 0, small positive heading big positive. Okay, so if we were going to graph the derivative, we have small negative, right? Small negative almost what? 0 to big negative. So let's small negative to almost to big negative, right? Small negative to big negative. You follow that? And then to the right of 0, we have big positive to small positive. So what is that going to look like on the right side? That's right, Jordan. It's going to be big positive to small positive, almost 0. Now that looks familiar. Does that kind of looks like 1 over x? What? Right, it did. It sure did. Well, this, let's think about it. So can you tell me if the slope from the left is going to equal the slope from the right here at x equals 0? We're going, if we go back up to our little statement here, we would say the slope as x approaches 0 from the left of f prime of x is negative infinity is not equal to infinity. Now, do you guys recall the power rule that we spoke about last time? No, we had a test, didn't we? No, we didn't. We had 3-1, right? I'm sorry. Okay, power rule. Do we remember that? Recalling the power rule? Because we don't want to have to use limits. We say if we have f of x equals x to the n. Do we remember what the derivative is? Power down, function, lower the power 1. Yes, very nice. So if my f of x in this case is course, putting things where they belong. You know what I'm doing with the negative exponent, right? This is going to be 2 over 3x to the 1/3, which is 2 over 3 cube root of x, right? Now, if we remember what our power functions were all about, if I have a negative exponent, is that what it looks like in the first quadrant? And then I have an odd root, so I can look to the numerator for its symmetry, and it's an odd function, right? But what's going on in this derivative algebraically? Can I plug 0 in this derivative? No. So the derivative is undefined here, isn't it? So it's not differentiable. F of x is not differentiable. What does that mean again? You can't take the derivative at, yes, Ian?
So these equations have derivatives, just not 0.
Right. So what is a derivative? You're right. Derivative is nothing but a fancy word for slope of the tangent line. So I have a tangent line to this function everywhere except at 0, because I don't know which to choose. Negative infinity or positive infinity doesn't even exist. What?
How do you justify that it's not differentiable?
First you have to prove it's continuous.
Okay.
And the second thing is you have to prove that the slopes from the left and the right
Don't equal each other.
Okay? Yeah.
So if a function was not continuous, then there would be no differentiable at the discontinuity.
At the discontinuity, but you can have slopes everywhere else. Yeah. Yeah. We call this a cusp. Maybe I'll be able to write on this. Maybe I won't. Ah, nice. All right, so it's not differentiable at x equals 0, but it's differentiable everywhere else. Do I have a slope of a tangent line at every other location? The answer is yes, and we call this, as I just mentioned a second ago, a cusp. Okay? Now, what's the difference between a corner and a cusp? A corner, two lines are coming together, right? A cusp is curvier. You've got two curves coming together. You notice they both come to points, right? It's not a nice, smooth transition. All right, the next one is the cube root of x. So let's graph this one. Here's the cube root of x. For differentiability, what has to happen? Your function must be check that off because we know the cube root is a function is continuous. And then we have to check out the slope. And I'm going to tell you this one has a problem at 0. From 0 from the left has to equal the slope. And 0 from the right. And then, whoops. So what's interesting about this character is let's write a representative for this one. We have f of x equals x to the 1/3, right? That's the function, the cube root. What happens at f prime of x here? derivative and see how it matches up with the function. This derivative here is a negative exponent, so what does it look like in the first quadrant, as we recall from power functions? Right, Sam, you're right. It looks like this, right? And then what do we do? If we have a cube root, that means you have domain on both sides, right? It'd be y-axis, and then I'm squaring it, so that means it has to always be positive, so it's got even symmetry on this side. Please draw for me. It's a little bit of a delay, but it's drawing. That's good, right? So what's going on at 0? Right. So what kind of tangent line do we have? We have small positives, small positives, small positives, and then we go to big positive, and then we actually have what we call a vertical tangent there at 0. And then we have these other microtangent lines here. We call this a vertical tangent. Doesn't like to write there, I guess. So I'm going to change that. And the tangent line goes vertical there. And the limit from the left equals the limit from the right, but it's headed where? To infinity, and the derivative doesn't exist there. And then Tegan alluded to the last one. So what's going on with this function? The red pattern is what? It's a, well,
It's the derivative of the value, right?
right, this is a piecewise, right? You would be correct. What would the piecewise be?
X equals 1 when x is greater than 0,
When x is greater than 0 and
negative 1.
when x is less than 0. So let's graph that. I should stay in blue since I'm... And x can't ever be what? 0 here, so it's going to be an open dot and an open dot. Can we have a tangent line there? First of all, what was the first thing we had to do for differentiability? F of x must be... Well, what happens here? Step 1, we have to say... We have to say no. It's continuous everywhere except where? Not at x equals 0. Do I have a derivative anywhere else? That means do I have a slope anywhere else? The answer is yes, right? So we can't go beyond this step at x equals 0. So it's not differentiable at x equals 0, but it is at 1, 2, 3, any number to the right of 0 and any number to the left. And I don't know why I put a graph on the bottom, but we'll just have to omit that. Alright. So where are this is a discontinuity, right, if we're going to list them? So what are the 4 places? Where are the 4 places we're looking for discontinuity, for derivatives to fail? Number 1, corners. Number 2, cusps. Number 3, vertical tangents. And number 4, any discontinuity. That's where they fail to exist. So I left this page blank because I wanted to make sure that we had covered the concepts here. So this is the first one. So I'm going to draw the conditions really quickly. We had the corner. We had the cusp. We had the vertical tangent. And then we had the discontinuity. And I'm going to make this statement. All differentiable functions are continuous. That's me. What about the converse? What does converse mean? Ooh. Yeah, so the converse is going to be, I'm going to make this statement to you. All differentiable functions are continuous, but can you say all continuous functions are differentiable? No. So, we can say that differentiability implies what? Continuity. But you can't say the other way around. That means if on a quiz or a test I say to you, f of x is differentiable from negative infinity to infinity, what am I telling you without telling you?
It's continuous.
That I'm telling you it's continuous. Okay? But if I say you have a function that's continuous from negative infinity to infinity, I'm not telling you anything about its differentiability, okay? So that's the first thing. So the converse is not true here. Big deal. That's a big, and what blows that away is the corner, right? The cusp and the vertical tangent. All three are continuous but are not differentiable everywhere, right? They have a problem somewhere. Okay? So the next thing is, and I kind of went through this. Differentiable functions, and I stress, what does differentiable mean? You can take the derivative and it exists, right? Differentiable functions are locally linear. Now, that's a concept here, and I'm going to use f of x equals x squared. Because this is a continuous function that I can take the derivative of everywhere, meaning it has no corners, cusps, vertical tangents, or discontinuities, right? It's a nice smooth polynomial. What happens if I zoom in enough on this function? If I were to, now I'm horrible at, taking this and, right? Somebody would do this and do this much better than me. And we're looking at the box. Huge. You see how I really botched it? I'm looking at that really closely.
Oh.
You know what I
see
mean?
what you're doing.
I'm blowing it up. Like, not literally blowing it up, but like,
With the big red button.
right?
Sorry.
Right, I know, with the big red button. Do you see? If I were to take a piece of this function and I zoomed in and 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 zoomed in, what does it look like? A line. Right? It looks like it could be a micro. Looks like it could be a micro tangent line. Right? So function that is differentiable, you could imagine as locally linear and made up of a bunch of micro tangent lines, right? Now, of course, the line goes on forever, but it's locally linear, meaning, you know, you could zoom in and zoom in and zoom in, and you'd see that part of the line. What about up here at x equals 0? If you zoomed in enough, would you ever see a line? You'd only see a corner, wouldn't you? If you zoomed in and zoomed in and zoomed in here, you would see a cusp or curvy part. You wouldn't see a line. Now here, technically, would you see a line? Except what's the slope there? It's undefined. Okay? So differentiable functions are considered locally linear. So if you zoom in on them enough that you can see that they are behaving linearly. Okay? The third thing. Believe it or not, we had an intermediate value theorem for functions. What do you suppose we have now? We have an intermediate value theorem for derivatives. Now, do you guys recall what the intermediate value theorem for functions was? Daphne?
The function is continuous. Every x has a corresponding y value. Kind of.
If it's continuous over a closed interval, it will have, yes, it'll have every y value between f of a and f of b. That means if you have a function that has y values and you're continuous and you are having y values between 1 and 10, that means you're going to hit every number on that number line between 1 and 10 in the y direction. You'll hit pi. You'll hit, right, square root of 2, square root of 3. Right? Of course, those are lovely numbers that you guys all think are obnoxious, but right, would you hit pi along your journey? So the y value would have to be that. So for intermediate value theorem for derivatives, so we say if a and b are 2 points in an interval on which, fancy language, f of x is, since this is for derivatives, on which f of x is differentiable, right? You know, I have trouble with spelling, but somehow I can spell differentiable every time without a problem. You know? Then, f prime, which means the derivative, right? Takes on every value between, what do you suspect? Instead of f of a, it's going to be f prime of a and f prime of b. Okay, now, what makes this significant? I'm going to delay on my board here, right? Is it going to draw it? It did. So let's go back to x squared really quickly. Here it is, x squared. And let's say f of x here is x squared. What is f prime of x? Using the power rule that we learned. 2x. And let's say I want to know f prime of negative 1. What do we get when we do that? That means the slope at negative 1. Negative 2, there it is, right? So that's going to be negative 2. And then I say, okay, well what happens, what about f prime of 2? That's going to be 4. Whoops, let's use yellow here because I'm feeling yellow. The intermediate value value theorem for derivatives says if you have a function that's differentiable, that means I can take the derivative everywhere, which I can, between -1 and 4. Do you agree? That's a nice smooth function. I have tangent lines everywhere, no corners, no cusps, no vertical tangents, and no discontinuities. I can find the slope everywhere. Then I have to take on every slope between -2 and 4. What's significant about that is that, what's in the middle? That means I had to have a 0 slope somewhere in this interval, right? And what's significant about 0 slopes? What's happening to the function when I have a 0 slope? Okay, it is changing direction, but we call it a minimum or a maximum is going on at a 0 slope. Do you see that? So if you know the slope is 0 somewhere in that interval, you know you've got an extrema of some sort, don't you? That's the powerful ramification of the intermediate value theorem for derivatives. Instead of, for the intermediate value theorem for functions, if you had two different y values, you knew you had to cross the x-axis at least once, right? Intermediate value theorem for derivatives says you had to have at least a 0 slope once, which means you have the possibility of an extrema, a max or a min, on that interval. That's kind of cool, maybe? A little bit? Like, yeah, all right. All right, so let's do an example here. Luckily for you, I have it printed out. So this is a graph of a function f that has a domain from -3 to 3, and it's composed of three different line segments. And what we're going to do is sketch the graph of the derivative on this xy plane over here. So can you tell me if there are places in this f of x function where the derivative won't exist? X equal where? -3, it will exist as an endpoint.
-2.
Okay, -2, correct? Where else? At 1? Alright, so what is the derivative? It's a graph of the slopes, right? And these lines have slopes. What's the slope from -3 to -2? 1. You could sound a little excited about that. So I'm going to put a solid dot here, and then when I get to -2, I'm going to be open, right? Well, I should be at 1. Let me redraw that. Right? My slope from -3 to -2 is 1. You see the slope of this line is 1, and now this represents the slope value. What about from -2 to 1? Well, we're going, and then over -5/3, which is roughly but it's -1.6, that's right. So we're going to go down 1.6, and we're going to have an open dot here, and then we're going to, I don't know if that's 1.6, but yeah, maybe it was. All the way to 1, and we're going to have an open dot there, right? Because it's not differentiable at 1, because we have a corner. And the slope, and that's going to be 5/2, isn't it? 1, 2, 3, 4, 5, and then we're going over 2, so that's 2.5 from 1 until 3. And that's the function of the derivative there. I mean the derivative. That's not too bad, right? If you have linear ones, you can sketch the derivatives pretty easily. All right, what about part B? It says name the x-coordinate of each point of discontinuity of f prime over that interval? Well, we can say at x equals -2 and x equals 1, right? So the derivative does not exist there. Does the derivative exist everywhere else? Meaning, do I have a slope everywhere else except for those points? Because at those corners, you don't know whether to choose the slope of 1 or -5/3, do you? What about here? You don't know to choose -5/3 or 5/2. Okay? Oops, going back. This is a classic AP Calculus question from 1986. How many years ago? Lots. 30. Alright, and this says, given this piecewise function, where a and b are constants, if a equals 2 and b is 3, is f continuous for all x? So this is how I would work this and show my work. I would say when a equals 2 and b equals 3, what's f of x? I'd show people what it is. It's absolute value of x minus 1 plus 2 for x less than 1. And then it is 2x squared plus 3x for x greater than or equal to 1. Now, your knowledge of absolute value functions, are they continuous? Your knowledge?
Oh,
Right? Would you agree that absolute value functions are continuous? So this is continuous left of left of 1. What about parabolas? So where's the only place I might be concerned? At 1. So I would say for continuity at x equals 1, because that's where I'm worried about it. And Ian, is there continuity on this page? The word continuity?
Yes,
Yes, there is. So what must we use?
Limit language.
Limit language. So this is going to be the limit. As x approaches 1 from the left of f of x, better or equal the limit as x approaches 1 from the right has to equal f of 1. So what happens here? Which piece am I going to use? The limit as x approaches 1 from the left. That's going to be the absolute value of x minus 1 plus 2 has to equal the limit as x approaches 1 from the right of 2x squared plus 3x has to equal f of 1. So what happens? So can I take the limit on the left here? I just use substitution. And what do we get on this side? 2. On the right side, what we get 5. Uh-oh, what happened? Boom, boom. So what we can say, therefore, f of x is not continuous at x equals 1, right? Everybody follow that? Part B says, describe all values of a and b for which f of x is continuous. Does part B use the word continuous? So Ian, do we need limits? We need the limit as x approaches 1 from the left, and that's going to be absolute value of x minus 1 plus 2 has to equal the limit as x approaches 1 from the right of, it was an ax squared plus 3x or bx?
Yeah.
Bx has to equal f of 1. take the limit on the left side. We figured that was 2. I plug 1 in. It's okay to speak. What happens when I plug in 1 here? We get A plus B. And f of 1 is just 2, right? Or is the equals on the bottom? It's on the bottom, so it's A plus B. So what does the question say? What conditions, right? What? Describe all values of A and B for which the function is continuous. So we can say for all such that, we can say that for all values A and B such that A plus B equals what? 2, f of x will be continuous. Is that all the values? That's all of them. What does part C say? So for what values of A and B is f of x both continuous and differentiable? So what has to be true at 1? Okay, so let's come up with for part C, let's come up with f prime of x. Well, let's write f of x first so I can remember what it is. F of x is equal to the absolute value of x minus 1, plus 2, right? For x less than 1. Ax squared plus, I want to put 3 so badly. Can you tell? Because we got that before. Bx for x less than or equal to 1. Can you guys, using the power rule, come up with the derivative for the bottom? A piece. Power down.
Greater than.
Yeah, it should. Thank you. I'm worried I'm losing you guys, so stick with me. What's the derivative of the bottom part using the power rule? 2ax, good. Plus b, that's for x greater than 1. Let's talk about the absolute value function here. Where's the break? At 1. So what is it doing? At 1, it's shifted to the right 1 and up 2, and does this, right? What's the slope on the left of 1? Everybody agree with that? And so that's going to be x less than 1. Now we have to check to see for differentiability what has to be true. Huh? It has to be continuous, right? So we know that f of x has to be continuous. Which means the limit as x approaches 1 from the left of f of x has to equal the limit as x approaches 1 from the right of f of x has to equal f of 1. Did we figure out for what values in part B made that true? What values? So we know that a plus b equals 2 will make that true, right? What else has to be true for differentiability? The limit as x approaches 1 from the left of the derivative has to equal the limit as x approaches 1 from the right of the derivative. So let's talk about that one. The limit as x approaches 1 from the left. That's on the left side is going to be negative 1, right? Correct? Equals the limit as x approaches 1 from the right of 2ax plus b. So this would be negative 1 equals 2a plus b. So do we have two equations and two unknowns? Yeah? Can we solve that? So what happens? We get a plus b equals 2. 2a plus b equals negative 1. I would multiply this top one by negative 1. And what do we get? Negative a minus b equals negative 2. 2a plus b equals negative 1. And then we can add them, and the b's go away, and we're left with a equals negative 3. And so b has to be, a plus b has to equal 2. So b has to be 5. So if you were grading this, or was being graded on an AP scale, you get 9 points for this question. So I suspect for part A, you get 1 point for the limits and 1 point for your analyzing, right? So that's 2. Part B, you get 1 point for the limits and then 1 point for the A plus B equals 2. How many are we up to? 4. For part C, you get a point for the expression of the derivative on the top and the bottom, so that's worth 2. So where are we up to? 6. You get a point for this, saying that it has to be continuous. You get a point for that. So where are we? And then you get a point for A and B. So how many points do you get if you don't have limits? 6 out of 9. Maybe even less. So it's important that we use the limit language, Ian. All right. Well, guess what? Your calculator will take derivatives. You know that, right?
Everything.
But we haven't looked yet at what our calculator does when they're undefined.
Is it just like
So we're about to find out. So can you guys see with the lights down low?
yes?
So let's do number 1, right? Because we had that graph. We had the corner, right? That was f of x equals the absolute value of x. And we know that it doesn't have a derivative at x equals 0. Okay? So what I want you to do is on your calculator, see what the calculator does when you try to take the derivative. So what happens is you're going to do D. How do you get there? You go to the calculus menu on the home screen, F3, number 1, or you can go second, number 8, right? Because that's the shortcut key to the derivative. Right, Sam?
Yep.
So what happens if the D opens? Now how do I get to the absolute value? You can go to the catalog, or what I would do is second alpha, and that'll put the alpha lock on. And then you can type in ABS, and then take the alpha lock off by just hitting alpha. I always type it. I don't ever go to the catalog. I go second alpha ABS. And the A is above the equals, the B is above the parentheses, and the S is above the 3. You see how many times I type it? You got that? And then we're going to put x here, comma, the derivative with respect to x, such that x equals 0. So I want you to do that on the calculator first. So what does your calculator say to you? What? Plus or minus 1. Now is that telling you the derivative doesn't exist there? Is the calculator saying, Ben, derivative doesn't exist there? Is it saying it? Is it spelling I choose? The answer is neither. The derivative does not exist there because it gave you two different slopes. And if you think about it, the derivative is slope of the tangent line. The derivative, being the slope of the tangent line, the tangent line has how many points? 1, right? And we had to use limits to get the slope. So for a limit to exist, the limit from the left has to equal the limit from the right. And we have a plus or minus 1 here, right? That's problematic. So the derivative does not exist. So the calculator brings you back this, and this means does not exist. I just want you to recognize what your calculator is telling you. And then what happens if you just want the straight out derivative? You go absolute value of x with respect to x. I want to know what that is, what that function is. Right. And it comes back with this language called SIGN of x. Well, that function is just this function that I put up here. It's this, and that, what does that mean? The slope on the left is -1. The slope on the right is 1. What was the other? This is for a corner. What was the other one we did? A cusp. You remember what that function was?
X to the 2/3.
So let's try that. The cusp, which was f of x equals x to the 2/3, and we know that it has a nice point there, and so we'll have the calculator do x to the, you have to use the caret, and you have to go 2 divided by 3, comma, x, close, such that x equals 0. What does the calculator say then when you do that? So it actually tells you there is no derivative there. So sometimes it'll flat out tell you. The calculator says here, undefined. And what does the calculator tell you the derivative is when you do that? Without at x equals 0. Does the calculator perform the power rule for you? What did it say?
2 over 3x to the 1/3.
2.
Over 3 times x to the 1/3.
So the calculator gives you the derivative. That's pretty cool, isn't it? 84 can't do that. Now the 84 will give you a numerical derivative, but it won't give you the actual derivative as a function. That's why this is a powerful calculator. This is the one that you want on deserted island. Right? What was the other condition we had? Vertical tangent. Remember what function that was? The cube root of x. So that's x to the 1/3. So the derivative x caret 1 divided by 3, comma x, close such that x equals 0. What does it say there? It says undefined. So sometimes it'll tell you undefined, and sometimes it won't. And I'm going to save going over piecewise for another day. Is that okay? And I think that's a lot, I know, but that's all I have.